we've already seen how it's possible to start with the displacement and take a derivative with respect to time to get velocity, take another derivative with respect to time to get acceleration. It's possible to go back the other way as well and start with acceleration and work our way back to velocity and then back to position or displacement. To do this, we start with our relationship, a is equal to dv dt, and we're going to integrate this. What that is that's performing antiderivatives. So it's whatever we were doing to take a derivative, we kind of go backwards to take an integral. One way of looking at this is we can multiply both sides by dt, and we get dv is equal to adt. We can now integrate this dv between some limits v naught to my final velocity v, and integrate my acceleration as a function of time from some initial time naught time 0 equals 0 to some final time t. And that'll work in general. For a special case where your acceleration is constant, the acceleration comes out front because it's a constant, it's not a function of time. So going backwards here, you just end up with a time dependence that you evaluate between your limits. And we get v minus v naught is equal to at. I know I haven't really explained how to perform these integrations so much. Just go with me on this. So this integral of dv gives you v, and then you evaluate between your limits. Upper limit minus the lower limit gives you v minus v naught. Same thing here, but with our t naught being 0, we end up with t. We can rearrange this and say that my final velocity is now equal to my initial velocity plus acceleration times time, and that's exactly what we got looking at our constant acceleration relationships, which is good, it agrees. We can now do the same thing for velocity. And take our velocity kinematic relationship that relates velocity to position and rearrange that to say dx is equal to v dt, integrate between our limits, and for constant acceleration, we can plug in this result that we got from constant acceleration here. And now we can evaluate this. This is now a function of time. And in evaluating this, we've got a constant v naught. To go backwards on the power rule stuff from derivatives, you would add to the exponent. So here we add to the exponent. There is no t here, so you get a t. So you get v naught times t. And then the second term, you have at. You add to the exponent. So t to the 1 becomes t to the 2, or t squared. And then you divide by the result. So you end up with v naught t plus 1/2 at squared. We can rearrange this, and we get what we got before, which is a relationship for constant acceleration. X is equal to x naught plus v naught t plus 1/2 at squared. So that's good. It agrees with what we did before. It gives us some confidence that this technique makes sense. But the powerful thing about this is now it lets us deal with things that are not just constant acceleration. We can deal with an acceleration that might be some function of time using this technique. And we'll show you that. Let's say we have this motorboat, and it's traveling at a constant velocity of 5 meters per second when it starts to accelerate opposite the direction to arrive at the dock. So its acceleration is -1/4 t. What's the velocity function of the motorboat? We'll start with, for this part A, our acceleration is equal to -1/4 t. And acceleration is also equal to dv dt. So we'll rearrange that and say dv, multiplying both sides by dt, we get dv is equal to -1/4 t dt. We can now integrate this. So we'll integrate from some initial velocity of 5 meters per second to some final velocity. We'll integrate here from some initial time to some final time. In doing this, integral of dv gives you v, evaluated between your limits of v and 5. We end up with v minus 5 meters per second. And then on the right side here, we add 1 to the exponent, so we get t squared, and then we divide by the resulting exponent, so divided by 2. So you get -1/4 divided by 2, or times 1/2, t squared. and then we evaluate this from 0 to t. And again, if you're concerned about this, t being the same t, just treat one of them as a dummy variable, and then we evaluated this. So this gives us negative 1/8 t squared. So this tells us, when we rearrange this, that my velocity as a function of time, adding 5 meters per second to both sides, is going to be 5 meters per second minus 1/8 times the time squared. And just to be clear, there should also be units on this term here, but since we didn't start off with units on this term here, you can just assume that the result of this, whenever you plug in here, should end up with meters per second if you plug in time in seconds. What time does the velocity reach 0? Well, we have a function. I want to know when this function equals 0, so I can set my value of my function equal to 0. Maybe I'll even write this. We'll set velocity equal to 0, and then we'll solve for time. So 0 is equal to 5 minus 1/8 time squared. We do some algebra, adding the 1/8 t squared to both sides, multiplying by 8 to get rid of, here, I'll do an intermediate step. So 1/8 t squared equals 5, and then we'll multiply both sides by 8. That cancels out the stuff on the left, and now we take a square root, and we can say that my time should equal the square root of 5 times 8, or 6.3 seconds. Last thing, what is the position function of the motorboat? Well, we start with what we had before. Velocity is a function of time, and that's going to be equal to dx dt. So we take the derivative, or we go backwards, we take the integral of this, and we say that dx is equal to v dt, where that v is now 5 minus 1/8 t squared. We integrate as before from some initial position to some final position, and from some time 0 to some final time. We can now try plugging this in. If we say that our initial position is 0, so what's the position function? We have to specify an initial position, or we'll have some constant there for what that is. And evaluating that, we get x on the left, and on the right, we get 5t minus the 1/8 times, so here the t squared, we add 1 to it, it becomes t cubed, and then we divide by the resulting exponent, divide by a third, so it becomes 1/8 times a third, or 1/24. See if I can write 4 correctly. Close enough. T cubed. And then we evaluate this from 0 to t. The 0 just disappears because when you plug in a 0, those go away. And so now we have my position as a function of time. Like so.